Just let's open the
start the PowerPoint. So I will give you a little bit of a break already before the coffee break. I'm not going to talk deeply about the science, but to tell you about this network of science which has helped to sponsor this particular meeting. Also will sponsor the school that Ivan Smolyuk and others are organizing starting at the end of the month in China. And has also contributed greatly to Ivan's career, and we're very proud of what we've been able to help Ivan with and how much he has contributed back to us. So this is the Institute for Complex Adaptive Matter, and we're focused on the topic of emergence, which, oh boy, hard to read that. Emergent phenomena are phenomena that owe their existence to the interactions between many subunits, but whose existence couldn't be deduced from a detailed knowledge of those subunits alone, at least in an easy fashion. One way to understand emergence is how can a collection of molecules think about what molecules are? And we define complex adaptive matter as materials exhibiting emergence. Some examples would be novel superconductors, such as the iron pnictide superconductors, amyloid assemblies of proteins, and liquid crystals, liquid crystal colloid mixtures, and liquid crystal defect structures. So the mission of ICAM is to search for the organizing principles of emergence in complex adaptive matter. And we believe that those have to be experimentally driven. Not that theorists don't have a role, they clearly do, but we always seem to need to have new experiments to show us new ways to interesting phenomena. And as far as the institution, it's rather emergent itself. It's basically an institution which has no walls. We are defined by the presence of our branches, and we now have of the order of 60 branches all over the world. The little pinpoints on the map here show you where those branches are at. We expect to add a few more branches this year. With the economy being what it is, we also expect to drop a few branches. But this gives you an idea of our international scope. So the idea is that we're a scientific network interlinking all of these branches all over the world, which represent either individual institutions or consortia of institutions, such as the 7 institutions involved in the Paris branch. And where do we get our funding? Well, we were happy that we just got renewed for 5 more years for our International ICAM Award from the National Science Foundation at about $1.05 million a year. We get contributions from each of our branches. To become a branch, you agree to commit to about $10,000 of ICAM-related activity at your own branch and $10,000 to our central fund. And you can view that as an investment on which the return is something like 2 to 1, if you decide to participate at least. And we have foundations that contribute to our outreach efforts. So on total, we have about $1.6 million a year of funding. Wow, this is really hard to read. I'm sorry, it looks better on my Mac. We had to convert it to the PowerPoint. Let's see. We fund exchange awards for junior scientists to carry out 2 to 12 months of research. We fund fellowships for collaboration with postdocs. For 2 years, you join 2 branches together with a postdoc. And 1 year for senior scientists. Those fellowships can go for up to $25,000. The travel awards and exchange awards can be awarded at any time, but these fellowships are awarded in an annual competition. We have travel awards that I just mentioned, which are for short research trips. We have exploratory workshops, which are somewhere between 5 to 10 per year, and we can decide those very quickly. Our Science Steering Committee, which examines those, meets quarterly. We have schools. There's an annual school in Cargés, and thanks to our renewal, we'll have an annual school in Rio de Janeiro, an annual school in Bangalore at the JNCSR, and the annual rotating school on complex adaptive, the College on Advanced Materials for Photonics. Ivan is very clever with acronyms. Now that the sun is coming in, it's even harder to read this. That's an emergent phenomenon as well. Let's see. Sorry, what are you doing? Can you just go back? Okay. Yeah. Oh, okay. I'll just read them out loud. So we also have outreach activities, and we have web hosting for our community. Let me just show you a little bit more. The main science thrusts are in soft matters, such as the topic of this particular meeting. We have a lot of interest in biological matter, and we have interest in quantum matter, which would be, for example, exotic superconductors and the cold atom traps. Overall, over the 10 years or so of ICAM, we've had well over 100 publications related from ICAM-related work, including several in Nature, one in Science, and several in the Proceedings of the National Academy of Science. This gives you an example of something that we consider to be sort of a quintessential ICAM-supported work. In this case, this cover story on science tells you quite a bit of science, actually. This picture down below is a topographic map of a high-temperature bismuth, strontium, calcium oxide superconductor, and this is what was discovered using low-temperature low-temperature scanning tunneling microscopy in the Seamus Davis lab at Cornell. So the situation was that Kazuhiro Fujita went from the University of Tokyo with some of the best samples of the superconductor to Seamus Davis's lab at Cornell on one of our ICAM Exchange Awards, where he learned how to do these particular measurements. And while it may not look like it, because it looks like it's fairly ordered, in fact there's significant disorder in these yellow lines, which are a measure of the disorder, intrinsic disorder, nanoscale disorder, the electronic density on the surface of this high-temperature superconductor. Completely new phenomenon. Nobody expected this particular phenomenon to be discovered, and it's really not understood yet where it comes from. And the point about comparing it to the topographic map is that if you look at the defect structures in the topographic map, they don't correlate well with the density modulations. So this is an example of emergent phenomena made possible by one of these I2CAM exchange awards for Kazuhiro Fujita. And interestingly enough, some theorists, Georg Schmalian and Peter Walnes, who hadn't met each other until they got together for ICAM, had come up with an idea that might have something to do with this called electronic mayonnaise. You know about mayonnaise as soft matter, where it's basically a microemulsion of egg whites with vinegar, where the of oil and vinegar, basically, where the egg whites serve as the glue to keep those disparate quantities intact. Well, the idea of Georg Schmalian and Peter Walnes is that you can do the same thing with doped electrons in a high-temperature superconductor, where these dark regions might represent the sort of regions of relatively high electron charge that correspond to the insulating phase, and these light regions would represent the phase of low electron charge corresponding to superconducting regions. And you can actually get a sort of nanoscale mayonnaise out of that. Whether this applies to Seamus Davis's data or not yet, we don't know, but it's an intriguing idea. This was a school on biological physics at Rio de Janeiro, held last year. And just to give you an idea, we had contributions from biologists, from biophysicists, biological physicists, and of course many of our schools are held in interesting locations. That's on Corcovado, looking out over the Bay of Rio de Janeiro. This was from a workshop sponsored last year at Boulder, Light Control of Liquid Crystal Adaptive Matter, a very successful workshop organized by Noel Clark and Ivan Smolyuk, which included other components of ICAM, such as a large amount of outreach to underrepresented groups, outreach to the community, industrial participation. A number of the sponsors were coming from industry, and live webcasting, as we're having at this meeting right here. And of course, I2CAM is rolling into the International College on Advanced Materials for Photonics, which will be in Boulder, next year it will be somewhere other than Ukraine, but back, I guess, in 2012, and China this year. This gives you an idea of how we've networked different branches together through our exchange awards. Oops. And so you can see that we sort of have this nice spaghetti, linking all of our different branches together via these exchange awards. And the rules on the exchange awards, which might be of interest to junior scientists or to senior scientists, are you can apply at any time. They support per diem and travel for 2 to 12 months for people within 5 years of their PhD. It has to be between 2 different groups. It requires a proposal, a CV, plus 2 letters of support from home and host mentors. But you can also have a mentor-driven exchange award where the mentors decide to write a proposal and then find a young scientist to fit the bill. And most of them are from the U.S. to non-U.S. or from non-U.S. to the U.S. There's a limited number within the U.S. and from non-U.S. to non-U.S. branches, if that makes sense to you. And these are the same things with our Junior Travel Awards, which are for short visits. And here's the spaghetti for Junior Travel Awards. And those you can apply for at any time. Oops, you can apply for those at any time. They're restricted to postdocs and graduate students. You just need a brief proposal with a letter from your mentor. For international travel, it's $2,500 towards whatever you need for your trip. And for some meetings, we'll accept block proposals, such as for this meeting, from the organizers, which give targeted blocks of travel awards that are examined by our Science Steering Committee. Most of those are also between the U.S. and non-U.S. or non-U.S. to the U.S. They involve a leg in the U.S. A limited number are available within the U.S. and between non-U.S. branches as well. Okay, and then we have a lot of outreach. We're developing an online science museum describing emergence in matter, which we hope to unveil either next month or shortly thereafter. We have some online short videos of ICAM scientists explaining their work. Yvonne, along with some others, are developing these emergent labs, which are modules to be handed out to high school teachers in order to explain emergent science at the high school level. We have an online journal club blog where leading condensed matter scientists comment on current papers. We have Music of the Quantum, which involves interviews with scientists on quantum matter. And we have ICAMopedia, which is sort of an ICAM answer to Wikipedia, although we're much smaller than Wikipedia. So if you want to know the website is ICAM-I2CAM.org, and my email is cox@physics.ucdavis.edu. But we would love to be able to reach out to this part of the world as well. We currently don't have any branches in each